Right now, invisible waves of energy are smashing into you from every direction. Every word you hear, every note of music, every crash, every whisper, they're all just air molecules slamming into your eardrums thousands of times per second. But here's the strange part. Nothing is actually traveling toward you. The air between you and whatever's making that noise, it stays right where it is. So if nothing moves, how does sound get from there to here? That's what we're about to find out. Sound is one of the sneakiest things in the universe. It's pure energy, traveling through matter without actually carrying that matter along for the ride. Think about it like this. Imagine you're sitting at the end of a long row of people, and someone at the other end pushes the person next to them. That person bumps into the next, who bumps into the next, all the way down the line until the last person gets shoved. But here's the thing, nobody in that line actually walked anywhere. They all stayed roughly in place. The push traveled, the people didn't. That's exactly how sound works. If you've ever played with a slinky, you've already seen sound in action. Stretch a slinky out across a table and give one end a sharp push. You'll see a wave of bunched up coils race from one end to the other. That's called a compression wave, or a longitudinal wave if you want to sound fancy. The wave moves forward, but the coils themselves just bunch up and spring back. They don't travel with the wave. Sound works the exact same way, except instead of metal coils, it's air molecules getting squished together and bouncing apart. Every sound starts the same way. Something vibrates. A guitar string wobbles back and forth. Your vocal cords flutter together. A speaker cone pumps in and out. When that vibrating object pushes outward, it shoves the air molecules right next to it closer together. When it pulls back, those molecules spread apart. This happens incredibly fast. A guitar string playing a middle C note vibrates back and forth about 262 times every single second. Each vibration creates another compression wave, rippling outward through the air. Once those first air molecules get shoved, they crash into their neighbors. Those neighbors crash into their neighbors. And on and on and on. It's a molecular chain reaction, like the world's fastest game of bumper cars. But unlike dominoes, which fall and stay down, air molecules are springy. After they bump into their neighbor, they bounce right back to where they started. They're ready for the next compression wave coming through. This is why you can hear a continuous sound, not just a single pop. The air resets itself almost instantly, ready to carry the next wave. So sound is really just alternating zones of crowded air and spread out air. Scientists call these compression and rarefaction. Compression is where molecules are squished together, creating a zone of higher pressure. Rarefaction is where they've spread apart, creating lower pressure. A sound wave is just these high pressure and low pressure zones traveling through the air one after another, like an invisible accordion stretching and squeezing. Loud sounds have bigger pressure differences. The molecules get squished much harder and spread much farther apart. Quiet sounds? Barely any difference at all. Just gentle little nudges. Now here's a fun question. How fast does this chain reaction travel? In room temperature air, sound moves at about 343 meters per second. That's roughly 767 miles per hour. Fast, but not instant. You've seen this yourself if you've ever watched fireworks from a distance. You see the explosion first, then a moment later, you hear the boom. Light travels so much faster that the flash reaches your eyes almost instantly, but the sound wave takes its sweet time, bumbling through the air molecule by molecule. But 343 meters per second isn't set in stone. The speed of sound changes depending on the air temperature. In hot air, molecules move faster on their own. They're already jittery and excited, so when a compression wave comes through, they can pass it along more quickly. In cold air, molecules are sluggish. They take longer to bump into each other. On a freezing winter day at minus 20 degrees Celsius, sound slows to about 319 meters per second. On a scorching summer day at 40 degrees, it speeds up to about 354 meters per second. And air isn't even that great at carrying sound. Water carries sound about 4 times faster, at roughly 1,500 meters per second. Steel? About 15 times faster, nearly 6,000 meters per second. Why such a huge difference? It comes down to how close the molecules are packed together. In steel, atoms are locked in a tight crystal grid, practically shoulder to shoulder. When one atom vibrates, its neighbor feels it almost instantly. In air, molecules are far apart, floating around with lots of empty space between them. The message takes longer to pass along. This is also why there's no sound in space. Space is an almost perfect vacuum. There are virtually no molecules out there to carry compression waves. If a star exploded right next to you, you wouldn't hear a thing. All those science fiction movies with dramatic space explosions going kaboom? Completely fake. In reality, the vacuum of space is the quietest place imaginable. Even if you screamed at the top of your lungs, the sound waves would have nothing to push against. Your voice would go absolutely nowhere. Back on Earth, not all sound waves are created equal. The number of compression waves that pass a point each a second determines the frequency, which your brain interprets as pitch. A big, booming drum might send out only about 80 waves per second. A high-pitched whistle might produce over 10,000. A mosquito buzzing near your ear? That annoying whine is around 600 waves per second. Humans can hear frequencies from about 20 all the way up to 20,000 waves per second. Below 20, you feel it more than hear it. Above 20,000, only dogs and bats can pick it up. Frequency is connected to wavelength, which is just the distance between one compression zone and the next. Low-frequency sounds have long wavelengths, sometimes several meters. High-frequency sounds have tiny wavelengths, just a few centimeters. And here's why that matters. Long wavelengths can bend around obstacles. That's why you can hear the deep thumping from a party down the street, but the vocals and high notes get blocked by buildings. Low-frequency waves are so big, they just wrap around corners like they're not even there. Short wavelengths travel in straighter lines and get absorbed or reflected by walls and objects. Now, what happens when something moves faster than sound itself? Normally, an airplane sends sound waves out in all directions as it flies. Those waves spread ahead of the plane, warning the air that something's coming. But when a plane hits the speed of sound and pushes past it, it outruns its own sound waves. The waves pile up and stack on top of each other, forming a massive cone of compressed air called a shock wave. When that shock wave reaches you on the ground, you hear it all at once as a single thunderous crack. That's a sonic boom. So sound waves travel through the air and eventually reach your ear. But how does your brain actually turn bumping air molecules into music and voices and laughter? When compression waves enter your ear canal, they hit your eardrum, a thin membrane that vibrates in response. Those vibrations pass through 3 tiny bones, the smallest in your entire body, which amplify the signal. Then the vibrations enter a fluid-filled spiral called the cochlea. Inside, thousands of microscopic hair cells sway like grass in the wind, each one tuned to a different frequency. When they sway, they send electrical signals to your brain, and your brain assembles all of that into what you experience as sound. So the next time you hear anything, a friend's laugh, your favorite song, rain tapping on a window, remember what's really happening. Something vibrated. That vibration pushed air molecules into their neighbors. Those neighbors pushed theirs. A chain reaction of tiny collisions traveled through the air at over 700 miles per hour and slammed into a membrane in your ear thinner than a sheet of paper. 3 bones, smaller than a grain of rice, amplified the signal. Thousands of hair cells converted it to electricity, and your brain turned all of that into something meaningful. All of that happened in a fraction of a second. Every single time you hear anything at all. If you like this video, check out one of these, and don't forget to subscribe.